This is a video about stoichiometry. This is the first time that you've done stoichiometry, and I'm going to try to introduce it to you in an easy manner. So we're going to look at stoichiometry, which is really looking at the mole to mole ratio in a balanced chemical equation, and then we're going to be able to do stoichiometric calculations. So reaction stoichiometry is looking at the relationships between different substances in a chemical reaction. This definition says reactants and products and mass. It can really be anything on any two substances in a chemical reaction that you can then determine how much you're going to need to react, or how much is going to be produced or left over. So it's a way to really quantify the amounts in a chemical reaction. So if you don't have your mole map out, I would go get it. And then we're going to be using this and just building on. So we already know how to go and use Avogadro. So we know there's that many molecules or atoms are in a mole. And we can write that in different, ways, with one on the top, one on the bottom, and reverse that. And here we know we're going to use whatever the molar mass is from the periodic table. But the new part is right here. So now, and I'm going to show you how to use this, we can make a mole-mole ratio. And what we do is I'm going to put a little box because it'll depend on the coefficients from the balanced chemical equation. But it'll be the moles of B if you're going to be going over here to B, or what your unknown is, over the moles of A, or what you've been starting with over here. And then once you get to the side, it's still the same. We still use Avogadro here. I'll use molecule this time in 1 mole. And then we're still going to use molar mass when we're doing this type of conversion over here. So let me show you how it works. So if you guys remember the reaction that we did in the fume hood where we burned the magnesium metal. So the first thing I want to do is I'm going to write the balanced chemical equation. So I was taking magnesium. I reacted it with oxygen in the air by putting it into the Bunsen burner. Now I'm going to balance charge, and now I'm going to balance the equation. So I would need a 2 and a 2. So the mole ratios are looking at these coefficients now. Assume there's a 1, even though we don't see it. These are now going to be interpreted as moles. So I can say I have 2 moles of magnesium for every 1 mole of oxygen that are going to react. Or I can flip that, 1 mole of oxygen for every 2 moles of magnesium. And then I can compare the magnesium to the magnesium oxide. So I have 2 moles of magnesium for every 2 moles of magnesium oxide that are going to be produced. And then I can also write that mole-mole ratio is what I'm doing. I can write it, I can reverse it. And then I think the last set of mole ratios would be, I have for every 1 mole of oxygen that is reacted, I'm going to get 2 moles of magnesium oxide. Or I can write this with the magnesium oxide on the top and the oxygen on the bottom. So that's what a mole ratio is. It's a conversion factor that's going to allow us to relate any two substances in a chemical reaction. They could both be reactants. They can be a reactant and a product, or if you had more products, they could both be products. So let me show you. Here is an example. So in the question, we're being asked for moles of the Fe2O3. So this is my substance that I'm going to try to figure out. This would be my B, if we're going to do the B and the A, using the mole map. And then I'm starting with 15 moles of aluminum. So that would be my A. So if I use my mole map, I'm starting here with my moles of aluminum, my 15 moles. And then I'm going to switch over and go across and figure out my moles of B, which will be the Fe2O3. This is the thermite reaction. It's a really exothermic reaction. So how do I solve the problem? Just like I did mole calculations, I always want to start with that beginning substance on the far left of the problem over 1. Then, so I'm right here, and now I'm going to cross over. Remember, I said I was going to use a mole-mole ratio, putting boxes where the coefficients are going to be from the balanced chemical equation. I'd have the moles of B over the moles of A. And this is dimensional too. So if I put, so I'm going to use the 2 and the 1. There's really a 1 here. I want to put the 2 on the bottom because then I know that my moles of aluminum will cancel. So this is kind of why I've always, a lot of times I include what substance it is when I do mole calculations because of this, because it kind of was leading up to this. And then I would put the substance of what I'm looking for, which is B, which is the moles of the Fe2O3. So you can see my moles of aluminum cancel, and I end up with moles of Fe2O3. So then when I calculate this, it's going to be 7.50 moles of Fe2O3. So I'm doing sig figs based on this beginning number. Let me show you another problem. So this is a problem with a reaction that is done in different spacecraft and in the space station, where we've got a lot of carbon dioxide buildup because of people living in the enclosed area, and there's really nowhere for that carbon dioxide to go. So what we do is we actually react it, and we react it with lithium hydroxide to form lithium carbonate and water. So the question is, how many grams of then the lithium hydroxide are we going to have to pack? You know, how much would be required if 880.2 grams of carbon dioxide on average, an average adult is going to exhale per day? So what we're doing is, I'm going to grab my mole map and make it a little bigger so you guys can really see where we're going. Or not. Okay. So we are starting with our grams of A, which would be the carbon dioxide, and we're going to want to convert that into moles of carbon dioxide. Then we're going to use the mole-mole ratio to get to the moles of lithium hydroxide, and then lastly we're going to calculate the grams of lithium hydroxide. So you can see kind of where we're going to go here. So when we solve the problem, we would want to, start with that beginning number always. So there's that many grams of carbon dioxide on average that a person exhales. And then I do need the molar mass of both of these. So I'm going to pause the video and let you guys calculate those, and then I will also have them available. So I just went and grabbed those molar masses. You don't have to show your work for molar mass anymore. I just go, when you calculate them to the hundredths. So just a reminder, this was my B, what I'm trying to convert to. This is my A. The molar mass are down here. You only need them if you're going to go from grams to mole or moles to gram, but we are going to do both for this problem. I'm also going to, it's going to be a bigger problem, so you guys saw on the mole map where we're going. I'm going to move that kind of out of the way though. Not enough room. Like I need a double slide. Let's see. Maybe I'll get rid of the astronaut person. Okay, so I'm going to move that over here. So here we go. 1 second. All right. Sorry, you guys can definitely fast forward me if you need. Okay, so the molar mass, I'm going to go from grams to mole for the carbon dioxide. It's 44.01 grams of CO2 in 1 mole of CO2. so I can cancel the grams. Then I'm going to go do my mole. So the next step I'm going to have, I like to put boxes around them. You don't have to, but that really reminds me. This is the only time I'm going to use the coefficients in the balanced equation. The only time where we might have a number here other than 1. We may have a 1 too, but like when you're doing these steps, it's always per 1 mole. These might not have a 1 in them. So now I'm going to put my 2, because I want to convert to lithium hydroxide, so 2 moles of lithium hydroxide, and then there's an implied 1 there, so for every 1 mole of carbon dioxide. So then you can see the moles of CO2 cancel. I'm at moles of lithium hydroxide, so I'm right here sitting around, but now I got to keep going. I'm going to go one more step, and now I'm going to use my molar mass of lithium hydroxide, which is 23.95. So there's that many grams in a mole, 1 mole always. And then I would calculate this. And again, you can see my moles cancel. I'm in grams. Once I do the calculation, hold on one second, I will do it for you and we'll sig fig it. Okay, so the answer ends up being 958, and then with 4 sig figs, 0.0 grams of lithium hydroxide. So per person per day, we would want to pack at least, we won't want to run short, would we? 958.0 grams of lithium hydroxide.